Welcome everyone to the 2DCC webinar series. Today we have Dr. Shulong Yang. He's an assistant professor of molecular engineering, and today he will be talking about multi-resolution photoemission spectroscopy on quantum materials. Dr. Yang is also a user of the 2DCC, and I think he'll mention some of that in the talk for portions of his work. Please go ahead.
Thank you, Kevin. Thanks for the invitation to giving this webinar. I'm very happy about my ongoing collaboration with my colleagues in Penn State and 2DCC. And today, some of the works will reflect on our ongoing collaboration, and I hope you'll find it interesting. So to just get started, I'd like to acknowledge all the collaborators in the last few years, without whom our work could not be completed. And this is really a long list because I've been doing work in various places. My PhD work was done at Stanford with Professor Ziyak Shen's group, and I collaborated heavily with scientists at SLAC, led by Wei-Xing Li, and our theory colleagues led by Professor Tom Deverell. During my PhD, actually, some of my samples were actually grown by other people. Later, I started growing samples myself, but back then, my samples were grown by a team led by Dr. Rob Moore. And later, as some of you might know, I moved to Cornell for my postdoc, and I started to become an MBE person, and I was in Professor Darryl Schlum and Kyle Shen's group. For the work that we had with, in collaboration with 2DCC, the samples were grown. Oh, okay, something is happening, but okay. The samples were grown in Professor Zhiqiang Mao's group. We received a lot of theory input from Professor Chaoxing Liu's group and Professor Binghai Yan's group from Weizmann. I'd like to also acknowledge my own group. This is really a pretty exceptional group of young researchers, we started 2 years ago, and it's still sort of at a developing stage. But I'm very proud of what we have done, especially during the COVID times. And what's kind of interesting is, we had to get some work done during the COVID shutdown, following the university regulations, and this is how we got things done. And you can, I took a picture back then when we were constructing our setup, and everybody, of course, was following the proper COVID regulations. It was just a very interesting historical time, and this is how we got work done. I hope everyone on this call is doing great with your university and your situation as well. Okay, so let's get started talking about science. So we are condensed matter physicists, and we want to, dig to the bottom of materials. And I would say that, a general perspective to think about materials is to think about the fundamental interactions between the different degrees of freedom. And this boils down to charge, spin, orbital, and lattice. Okay, and the interaction between these different degrees of freedom basically gives rise to all the fantastic strong correlation effects or topological order or other fancy physics. So let me just give you a few examples. The interaction between charge and spin degrees of freedom can lead to something called the heavy fermion systems, where the effective mass of electrons can exceed over 1,000 times of the free electron mass. The interaction between spin and orbital degrees of freedom give rise to something that we're very familiar with by now, which is the topological materials. And the band inversion is indeed facilitated by the strong spin orbit coupling. The interaction between charge and lattice, let me get to the lattice and orbital degrees of freedom. This interaction actually leads to a celebrated phenomenon in iron-based material called nematicity, where the interaction leads to the symmetry breaking from the C4 symmetry to the C2 symmetry. And there's an intertwined relationship between the nematicity and superconductivity. And finally, of course, between charge and lattice degrees of freedom, there's the interplay that leads to something what we call the charge density waves, which is a periodic pattern of charge density and lattice distortion. I should also mention that the interaction between charge and lattice degrees of freedom also gives rise to conventional superconductivity. And this interaction is the pairing glue to bind electrons into pairs. So basically, the job of condensed matter physicists can be simplified as just disentangle the interactions using different ways. And today, I would like to really emphasize, two particular perspectives. One is to disentangle interactions in the time domain. And why do we want to do that? It is helpful to look at all different kinds of interactions on both the energy and time scale. And as we know that energy and time are two conjugate quantities, which means that the higher energy scale you go to, the shorter time scale that corresponds to, and vice versa. So when you look at this broad range of energy and time scales, and you realize that different techniques can be suited for different kinds of interactions. So for example, for the high energy scale interactions, things that include screening effects, electron correlation effects, they typically happen on the energy scale of a couple EVs or a fraction of EVs. And this is usually the domain where energy resolved spectroscopy can be most suited with, because it's very easy to have an energy resolution, let's say for photoemission down to a couple millieV, and for other spectroscopies, I think 10 to 100 MeV is sort of a suitable energy resolution that most spectroscopy tools can get to. However, on the other regime, when you go to smaller and smaller energy scales, that also means your time scale goes larger and larger. And this is actually a domain where time resolved techniques can be kind of more useful, because for time resolved technique, it's the reverse philosophy that our time resolution, which is routinely obtained at around 100 femtosecond, can be actually more useful for resolving the smaller energy scale dynamics, which happens on the order of hundreds of femtoseconds or even a few picoseconds. So this is the first perspective. Sometimes by going into the time domain, you can disentangle interactions, especially at low energy scales, more easily. There's another perspective that I'm going to talk about today, which is the spatial domain. And in quantum materials, different kind of interactions often involve kind of a spatially inhomogeneous structure. So for example, the modern development of molecular beam epitaxy allows us to have spatial variation along the z-axis, and you can really build materials layer by layer. This also means if you want to disentangle interactions, you have to look at these interactions layer by layer. And I'm going to show you two examples today where that's actually really critical. And we can also have spatial variation in the XY plane. I'm talking about quasi 2D materials. And here I'm using an example from a recently published study on manganese bismuth telluride 1610, where you can really see that on a microscopic scale, there are domains which are of the size of 20 microns. And you really have to look at the electronic interactions within each domain. Otherwise, if you integrate over all domains, this will not be meaningful. So therefore, when we try to probe these interactions happening at different spatial scales, we have to combine a series of surface-sensitive techniques, including photoemission, electron diffraction, STM, and also bulk-sensitive techniques, transport optics and X-ray scattering. I'm talking mostly about hard X-ray scattering here. And sometimes even you need a really localized atomic resolution probe, which is provided by STM. So you really need to combine different techniques which probe things at different spatial scales to have a complete picture. So this is what motivated me to think about doing spatial and temporal engineering of quantum materials in this two-dimensional phase space. Along the horizontal direction, this is what I call the temporal engineering direction, where you could use femtosecond light to manipulate or engineer materials to tailor them in the time domain to have unconventional properties. And one of the iconic example, which was done by Professor Neil Geddick from MIT, was the discovery of Floquet block states in topological insulators. There, we could use the periodic potential from the optical excitation pulse to create replicas of the bands. So this is really the iconic feature of non-equilibrium engineering. And on the other hand, along the vertical direction, we can have spatial engineering, where you can build materials layer by layer or species by species. And you can tailor the material properties by building things from ground up. And I'm going to talk about some of my attempts recently to pursue this direction. But of course, there's also a vast phase space in between. For example, you can have the coherent control of certain materials where you do not really alter the ground state like what you do with Floquet block, but you sufficiently modify the material or the lattice so that you can make the lattice oscillate and make the energy scales oscillate as well. In this process, you can disentangle some of the interactions. On the other hand, you could also have metastable states. In these states, they do not really have time dependence, but it's non-equilibrium. So once you hit the sample with certain external stimuli, the material will transition into a different phase, but it's non-volatile. And of course, there's also the direction which I'm pushing for, which is a complete engineering of space and time, which requires the construction of novel tools and infrastructure. So I'd like to first use one example of demonstrating the spatial temporal engineering. And this is the famous example of monolayer iron selenide superconductors. So for monolayer iron selenide, by now it's almost been a decade since the first discovery. It's been pretty famous. By growing a monolayer of iron selenide, you can substantially enhance the superconducting TC. So today I'm going to show you the studies in the past few years where I really combined techniques in both the spatial and temporal domains to engineer and probe its material. Excuse me. So first of all, I did my study at Cornell University, where I combined MBE, ARPES, and transport to study both the spectroscopy properties as well as the transport properties from superconductivity. And then we could also look at a much finer, smaller spatial scale. So we actually go to an advanced light source at Berkeley National Lab to do a spatially resolved micron resolution ARPES. And this allows us to disentangle the inhomogeneity of iron selenide thin films. And of course, I was also able to do spatial engineering by doing time-resolved ARPES and time-resolved X-ray diffraction. And this was the work I did at Stanford. So you will see that all these different techniques will reveal some aspects of how you would engineer these materials. And we would have a comprehensive understanding of the material at the end of all these studies. So let me just start by talking about iron selenide. I already mentioned that it's an iconic system that shows the magic of interface. So by growing a monolayer on STO substrate, you can see this really interesting big superconducting gap when you do scanning tunneling spectroscopy. And this gap is significantly larger than what you would get from the bulk iron selenide, or even from just growing another layer of iron selenide on top. And of course, people also did all kinds of spectroscopy, including ARPES, to detail the evolution of the band structure as a function of temperature. And it seems the gap would actually persist up to 65 to 70 Kelvin. And today, I'm actually going to show you a comprehensive study that would put a question mark on the TC of the monolayer iron selenide. And you will see that by only using surface-sensitive ARPES technique or STM, this is not sufficient to truly characterize the superconducting state of this magic sample. So of course, this is a thin film sample, so I'd like to highlight that there are numerous opportunities for optimization. So for example, you could engineer the electron-electron or electron-phonon interactions. You could vary the film thickness. As a matter of fact, even a second layer does not superconduct. And you could also do surface doping to change the electron concentration on the thin film. You could grow the material on different kinds of substrates to tune the epitaxial string. And finally, the epitaxial growth of this material depends very sensitively on surface conditions of the substrate. So what kind of surface reconstruction or interface properties would also sensitively tune the properties. So this is the combined angle resolved photoemission spectroscopy and transport results on monolayer iron selenide. So let me just walk you through our studies. So the leftmost panel, this is a temperature-dependent false color map of the symmetrized ARPES spectrum. So the panel A and B are basically the same data, just A is the color plot. So this is basically taking, in ARPES terminology, we call it EDC, energy distribution curve. It's taking an energy spectrum at the Fermi momentum. And at low temperature, you see this iconic double peak structure. And this is due to the opening of a superconducting gap. And as you raise temperature, this gap becomes less prominent. And around high temperature, maybe up to 90 Kelvin, the gap starts to be not recognizable. And we could try to use the peak-to-peak distance plotted on the top right to indicate the gap closing behavior. Actually, I would like to emphasize that this is not quite a gap closing behavior. And what we have observed is actually a gap filling behavior, where the peak-to-peak distance basically stays unchanged until the spectral weight in the middle just fills up the gap. So it's kind of a very peculiar, unconventional behavior if you compare to conventional superconductors. But we see this gap at least all the way up to 70 or 80 Kelvin. And one could even argue that even at the highest temperature, 90 Kelvin, you see a very bizarre flat top behavior that may still be a gap. So this is the first peculiar thing. And then we performed in situ transport studies on the very same sample. And this is panel D on the right. And you see something that is really different from the ARPES picture. The resistance actually does not start dropping until about 40 Kelvin and only enters the zero resistance state about 30 Kelvin. So if we use the conventional definition of TC using transport studies, you could never end up calling a TC of 70 or 80 Kelvin. Instead, the TC is maybe at most of 40 Kelvin. So this posed a question. What is the actual TC of this material? What's happening with this material? So the first thing, of course, we have to ask ourselves as material scientists is to consider the question of inhomogeneity. The material is a thin film, and our transport studies, I have to tell you, is actually a macroscopic probe. We have a four-point probe, van der Pol geometry. It forms a square. Two leads are current leads, two leads are voltage leads, but the square has a side length of 7 millimeters. So it's really a macroscopic probe. And of course, the question is how homogeneous of the sample is across this many millimeters. So to answer this question, we have to look at different spatial scales, just to reflecting from my earlier discussion. We went to Advanced Light Source at Berkeley and performed the micron scale spatially resolved ARPES. And this is a two-dimensional map of such a superconducting gap. And you can see that there is some variation, but it's centered around 10 to 15 MeV for this gap. And if you actually do some statistics of the superconducting gap, you can see that this histogram that really has a very strong focus around maybe 13 MeV with a standard deviation of 0.8 MeV. So it's not totally homogeneous, but the spread is rather confined across many millimeters. And based on this result, we could do a simulation of what the inhomogeneity would do to your transport behavior. So for this, we basically just assume a certain distribution of, we basically take the distribution from the measured distribution of gaps and use that to superimpose different transitions at different TCs and just superimpose all these different TCs to get an averaged resistance versus temperature curve. And this is the red dashed curve at the bottom right. So this is what we sort of simulate based on the distribution of the gap energy. And you can see that the measured, the experimental transport data is still way, way broader than what the inhomogeneity would give us. So there is something more intrinsic to the spread of this transition width. So what is it? So on the other hand, let's also consider a different effect. Monolayer iron selenide is a 2D superconductor. So it's subject to something called the BKT transition in the 2D limit. And for those of you who know about this, this means that you can actually never get the true coherent microscopic superconducting state in 2D limit, but instead you get vortices. And at sufficiently low temperature, these vortices form vortex-anti-vortex pairs. And that indeed, even though that's not totally a homogeneous superconducting state, that has no dissipation. So you can still enter the zero resistance state. So this is what we call the BKT transition. It's deeply connected to superconductivity, but not exactly the same. And the icon, the signature of the BKT transition is the exponent of the IV curve. Basically, what's the power law when you plot the IV curves? And this power law exponent should go to 3 at the BKT transition. And this defines a transition temperature of roughly 27 Kelvin. We could also use a different metric to find this BKT transition, basically plot this ratio, this logarithmic of resistance as taking the derivative of it as a function of temperature. And if you plot this quantity, the extrapolated TBKT happens at 0 of this quantity, which happens around 27 Kelvin. So these are all sort of consistent. And also, let me remind you, consistent with the zero resistance TC defined over here, 29 Kelvin. So around 27 to 30 Kelvin is where BKT transition happens. It's where you enter a zero resistance state. So everything is consistent. And in addition, we also want to study the inhomogeneity or the effect of disorder by systematically study the sample quality dependence. This is often ignored in most of the studies so far, because people always try to present the best quality data, and that's human nature, and we understand that. But here, we actually take the initiative to really report a systematic sample quality dependence. We studied on the order of hundreds of samples, and we can find some systematic trend. And what we found was the superconducting properties are indeed sensitive to disorder, but not really the superconducting gap. The gap actually is largely unchanged as a function of disorder. So if you just measure ARPES, you would not know. However, the transport TCs, the zero resistance TC and the onset TC, they both decrease very sensitively with increasing disorder. The other thing that's worth mentioning is that doping is changed by very little amount. So actually, this is just about disorder, not quite the doping dependence. So we really need to understand what this disorder does to our TC and our TBKT. And can we actually push the sample to the cleanest limit so that we get the intrinsic TC of iron selenide thin films? And that's what we did. We try to compile all our data with different extent of disorder. We compile all of this data, and this is a 2 to 3 years of data that's plotted over here. And of course, I should say that it's not only my work; it's a teamwork within the Cornell team. And what we see is a very peculiar trend. So all of these different TCs, the zero resistance T0, the onset temperature for resistance drop T onset, and what we call the T delta or the T gap, they all have different disorder dependence. So as you change disorder, what you see is actually the zero resistance TC changes most drastically. And this is just want to remind you, this is the temperature where the resistance actually dropped to 0. So you can see that this changes very drastically as a function of disorder. Less so about the onset temperature, but it still changes. You can clearly see a trend of where the onset is going. But if we try to study the T delta or where the gap opens, it actually is less sensitive. It's mostly independent of the disorder. So what we discover from this study is that you cannot just look at T delta as a proxy for the onset of superconductivity. Instead, you should pay attention to the zero resistance TC as well as the onset TC. What's also kind of interesting is that if you plot the so-called residual resistance, when you extrapolate the normal state resistance down to low zero temperature, if you plot this quantity as a function of TC, basically, you can see that you only get superconductivity, which is under this blue area. You only get superconductivity when your residual resistance is less than a quantity called the quantum limit of a pair conductance or a pair resistance. And this makes sense because only when your residual resistance is lower than that, that means your disorder-induced scattering is not as important compared to your quantum conductance. And that's where your superconductivity starts to kick in. And the other thing that I also want to notice is that if you plot this zero resistance TC, if you extrapolate it to the cleanest limit, so let's assume that we can completely kill the disorder so that the residual resistance basically is zero. And the cleanest limit would give you a T0 of roughly 40 Kelvin. So that is basically the ultimate limit of iron selenide. It is a little frustrating because it's not quite high TC, but this is the intrinsic properties of this superconducting state. And only by going through this kind of effort, you can reveal this limit. The other thing that's also kind of interesting and remarkable is that between the T onset and the T delta, there is a substantial temperature difference. And here my colleague calls it a pseudo gap, and I think this can be misleading. So for those of you who study cuprates, I apologize. I mean, this is not quite the same pseudo gap as in cuprates. What we basically mean here is that this is a region where you do have a gap, and most likely it's a superconducting gap, but you do not really have a any macroscopic change of superconductivity in transport. And finally, let me make the final point. There's really a lot to learn from the study. The final point is that we can also compare these different TCs with the counterparts from the bulk materials. And by now, you probably see that it's actually not quite appropriate to compare T delta with the TCs from other materials, because in bulk materials, your T delta and TC would not be so different. So instead, we should compare with T onset and T0. And what is really interesting is that there are bulk materials. The latest example is the so-called TBA plus iron selenide. It is organically intercalated iron selenide bulk crystal, where the T onset is basically at the higher limit of all the iron selenide thin films that we have grown. To that extent, it's tantalizing to say that, indeed, you could achieve the same kind of microscopic superconducting state at its comparable temperatures, even in bulk iron selenide, if you give it the appropriate tuning. It raises a really important question of what the substrate does to the material, and I leave that to an open discussion. I should also emphasize that the kind of fluctuating superconductivity that we have discovered from iron selenide, it is actually quite a generic phenomenon. And I'd like to use this example from cuprates. Both of these studies are from bismuth 2212. And indeed, the same kind of phenomenology can also be seen from cuprates. So this is the most updated bismuth 2212 phase diagram that was discovered by the group where I did my PhD. And what I find interesting is that cuprates never get old. Even in the year of 2019, we're still drastically rewriting the phase diagram, and that's really fascinating to me. Basically means we knew absolutely nothing about cuprates. But anyway, so the interesting thing is, from this new definition, actually there is sort of a crossover region where you have superconducting gap, but it's not giving you a macroscopic coherent transport. This can also be seen from the transport studies on monolayer bismuth 2212. This was the work beautiful work done by Professor Yuanbo Jiang School from Fudan. And if you look at this transport curve and compare it with all these transport curves that I obtained from iron selenide, they are surprisingly similar. And you can always find this very broad regions where you see this bend down of the resistivity, but it doesn't immediately enter the zero resistance. So we believe that the same kind of BKT physics, the same kind of fluctuation also exists in quasi 2D cuprates. And now we have understood the physics, or we have some understanding of the physics. What about the engineering aspect? How do we engineer this material? And to reflect back on my earlier points, we could engineer this material both in the spatial domain and in the time domain. And this is actually the latest effort from my own group, led by Dr. Chen-Hui Yan, who is my postdoc. And he has been growing iron selenide on a substrate with vastly different lattice constants. Actually, this is on rutile TiO2 on the 100 termination. And this is a rectangular unit cell, a surface unit cell, would give you more than 20% of strain along one direction and negative 20% strain along the orthogonal direction, if the film can be epitaxially strained. And we have successfully grown this material, but I have to caution you that actually we discovered it's not quite strained. Actually, it looks like, it looks like the iron selenide is mostly not constrained at all by the TiO2, which means the interfacial interaction is not as strong as in the interface between iron selenide and STO. But nevertheless, it's an interesting control sample where we see substantially smaller doping. The doping is about 0.07 electron per iron as compared to an STO, which would be almost a factor of 2 bigger. And we have seen a substantially smaller T delta, T onset, and T zero. Everything is just downscaled. So we believe that this is more like a doping dependence instead of a strain dependence. And this is telling us that electron doping actually plays a really important role in tuning superconductivity in this material. And this is another really interesting direction for the spatial domain engineering. And I would say that this is a very preliminary data, so I'm happy to discuss it, but it's still at a very early stage. The idea is to grow an oxide, iron selenide oxide sandwich structure. The idea is very simple. If you have one single interface, you get a TC boost by 1 order of magnitude. What about I have 2 interfaces per iron selenide? Would I just double the interaction? Would that increase TC substantially? So with this motivation, we tried to grow this sandwich structure. So this was done at Cornell, but it's very, very challenging. And for those of you who know MBE, you probably realize that growing oxides on a chalcogenides is just intrinsically challenging because oxygen and chalcogens are basically mutually contamination. So this is an incredibly challenging experiment, but we have some progress. So the first thing we realized on sample number 1 is that ozone will kill iron selenide immediately. So ozone is not good. From the read pattern, you can see that you form islands and becomes just not good. For sample number 2, we tried not to use ozone, but we exposed it to strontium, and it turned out it's also extremely bad because strontium is really metallic. So you actually start to form strontium selenides. And the last attempt, which is marginally successful, is that we use molecular oxygen and titanium and try to grow TiO2 on top. And by now, we still don't know if how successful this growth is, but what we did was that we could do transport studies, and we saw that 2 things. First, the disorder is definitely increased, so that you do not really have the true zero resistance. So the sample is partially compromised. Second observation, the onset TC seems to increase a little bit. So whether that top interface does something to the film, that requires further work. And of course, we can also engineer iron selenide in a time domain. And this goes back to my PhD work when using time-resolved ARPES to study the coherent A1G phonon oscillations in this material. Iron selenide follows the iconic structure, this tetrahedral structure. where one iron is connected to 4 seleniums and forms a tetrahedron. And the strongest oscillation is the so-called A1G mode, where basically the selenium layers on top of the iron and below the iron, they are oscillating against each other. And you can directly see this oscillation in the electronic structure measurements. So on the left, the top left panel, basically I'm plotting the oscillatory photoemission intensity as a function of time. And I do this for different thicknesses. And I try to align their peaks and troughs. And what is very obvious is that I could not do this for later delays. And the reason for that is that there's actually a frequency shift. And it turns out that there is an abrupt but substantial, well, in terms of the absolute magnitude, it's not substantial, but it's a very abrupt frequency softening near the 1-layer limit. And this is actually due to the strain of the substrate. But this demonstrates that you could indeed use the A1G phonon to tailor the material in the time domain. And of course, we broadened the scope of the study and did not only time-resolved ARPES, but also time-resolved X-ray diffraction, so that we could resolve both the atomic displacement as a function of time, as well as the energy shifts for different orbitals. And this is what we call a coherent lock-in measurements, because basically you define a lock-in frequency using the atomic oscillation. And using this, we can directly compare the magnitude of the energy oscillation and the magnitude of the atomic displacement. This gives us a ratio, which is directly in textbook called the electron phonon deformation potential. What is really fantastic about this is that this is a theory-free approach, so that we can use this experimental value to directly benchmark the theoretical predictions with different kinds of input. And by now, this is actually old news, but what was really a breakthrough back then was we actually discovered that the DFT calculations did a really bad job without the strong electron-electron interactions. However, if you used dynamical mean field theory as an input for your density functional theory calculation, then you could actually recover this strong electron phonon coupling deformation potential. And this difference is not small. This difference is about 1 order of magnitude. This means that the electron-electron correlations actually substantially enhance the electron phonon interactions. So this is a substantially new understanding we obtained from the time domain studies. Okay, so I've gone in depth into these different kinds of studies, both in the spatial domain and also in the time domain. And we have learned that we need a better way to define the superconducting transition temperature for monolayer iron selenide. We need to look at things in a micron scale spatial domain. We need to look at the electronic structure in a femtosecond time domain. But what's really interesting about this approach is that it's really tedious. It's very, very challenging. To complete this comprehensive study, you need to access facilities in 3 institutions across the continent to perform spatial temporal engineering. You have to go to Cornell, Stanford, and Berkeley. And it's so tedious, it's time consuming, and one can ask the question about the comparability, whether these different results are actually comparable, because the matter of fact is that you have to carry the sample across the continent, and these are very sensitive samples. Even though you can cap it, you can put it into a UHV suitcase, whether the samples are still pristine enough for you to do the study. Can we do better? Can we realize this vision of spatial temporal engineering, but do it in a single lab? That is indeed my vision and what my group has been doing the past 2 years. We wanted to realize a multi-resolution spatial temporal engineering platform. We call it, in abbreviation, MERSTEP. We want to realize MERSTEP in our own lab. And that's what we did. In fact, this lab was fully established and optimized in November 2020, thanks to the hard work from my group members, thanks for the support of all the equipment vendors. Everybody has been working really hard through the COVID times, which I'm very proud of. And it's a very complex system. It's very powerful. And to appreciate it, I have to somehow give you a mini lecture on the ARPES. So just bear with me for a second. Angle resolved photoemission spectroscopy is by now a very established technique, but there are a lot of subtleties in this technique that we have to think about when we design the experiments. Especially, we want to probe in both the spatial domain and in the temporal domain. How do we do that with different kinds of flavors of ARPES? So ARPES basically has three key ingredients. You have to have a sample, you have to have an ARPES electron analyzer, and then you have to have light sources. The sample is given by our MBE chamber, which you can tune the materials for sure. The analyzer is basically given in our lab. There's not so much you could do with analyzer, except that our analyzer is pretty powerful. It has a deflection voltage functionality, so it makes the measurements much easier. But these things are sort of the things that you do not tune very easily. But there's so much that you can tune with the light source. And indeed, most of the functionalities of ARPES are actually defined by the kind of light source you use to do ARPES. So let me actually give you this example. So in our lab, we combine 3 different light sources with complementary capabilities to do different kinds of ARPES experiments. So the first thing is that we have a conventional helium lamp ARPES, which has fixed photon energies at 21 eV, 23, and 40.8 EV. And we also have a high resolution, high repetition rate laser source. This is based on the titanium sapphire oscillator. It's a very old technology back in the 1990s. This we can use to generate 6 eV pulses, but at very high repetition rates of 80 megahertz. And each pulse is relatively less energetic. We also have a broadband ultrafast laser system, which gives us orders of magnitude more pulse energy, but it's working at much less repetition rate, about 200 kilohertz. And from this laser, what we do is that we can use it for pushing the material into the non-equilibrium and perform time resolved ARPES experiments. So they really have different capabilities. And the table over here has a comprehensive comparison of these different capabilities. I'm not going to go through all the parameters, but let me emphasize a few interesting highlights. The helium lamp is the most direct way to do photoemission. It gives you a quick survey, so it has high photon energies, but everything else is basically not as good. It has a really big spot size, so it's a millimeter size microscopic probe. It has relatively low photon flux, a relatively not so good energy resolution. It has no time resolution whatsoever. It has no polarization control, and you do not have pulse laser at all. So helium lamp is great for just doing ARPES, but really you don't have much tunability. However, for our high resolution, high repetition rate 6 eV laser, the photon energy is tunable within a small range. The spot sizes can be as small as a few microns. So this actually allows us to do micro ARPES. The photon flux is basically unlimited, depending on how much pump beam you put into the VBO crystals. The energy resolution can be artificially good because you can limit the bandwidth. The time resolution is not so good, but that's not the purpose of this beamline. And you have full polarization control. Your repetition rate is 80 megahertz. And this is really in contrast to the low repetition rates time resolved beamline, where you actually do not have as good of energy resolution, and you probably do not want to focus because of the space charging effect. I don't have time to elaborate on that, but you don't want to focus too much. But this allows you to get a time resolution down to 35 femtosecond. So let me actually show you our commissioning experiments on this MERS step. And really the performance has been spectacular. And I compare our results, which are basically on the bottom row, to the results which are obtained from conventional setups. Some of them were obtained from my PhD lab, some of them were obtained from my own lab. And we can really compare the performances. And let me remind you, these are from basically the same material, this iconic topological insulator bismuth selenide. And you can see that the MERS step laser-based high-resolution ARPES is more than just revolutionizing the capability of ARPES. You can see that the sharpness of the surface state and the resolution is just fantastic. And our time-resolved ARPES, which is based on different principles of ultra-fast femtosecond lasers, we achieve a 35 femtosecond time resolution. As far as I know, this is actually setting a record, at least in North America, in terms of solid-state based nonlinear photonics-based time-resolved ARPES. And this is clearly exceeding what I have achieved in my PhD. And finally, we can focus the high-resolution laser light to as small as less than 10 microns. Actually, I do not really know how small the beam is, because you can see that we're really approaching the pixel size of the camera. The pixel size of the camera is 5 microns. So we have at most 2 pixels. That's what I can say. So we can really get fantastic spatial resolution at the same time. The machine is commissioned. And what do we do with it? I have about 10 minutes left. So I'll try to highlight some of the recent studies. And this is also reflecting our very successful collaboration with 2DCC. The samples were grown by Professor Zhixiang Mao. Theory was mostly done by Professor Chaoxing Liu. And I don't think I have enough time to go through all the prepared slides, but I'll try to highlight a few interesting results. And this is following exactly the vision I outlined at the beginning. We try to have spatial domain engineering and time domain engineering to try to understand a quantum material in a comprehensive way. And this magnetic topological insulator is really a fantastic platform for us to apply these multifunctional capabilities. So for topological insulators, why do we want to make it magnetic? And the underlying reason for that is that we want to induce broken time reversal symmetry. And when you break the time reversal symmetry, you can induce a broken symmetry gap at the surface state. And this will induce a topologically non-trivial edge state. This edge state is actually chiral. So basically what you're doing here is that you induce a quantum anomalous Hall effect. That's our grand goal. And to do that, you basically have to introduce some time reversal symmetry breaking in a topological insulator. And I want to remind everybody that this has been done on the regular topological insulators bismuth telluride, and that was actually advanced by our colleague in Penn State, Professor sorry, your name just slips out of my mind, but I'm just give me a second.
Zhiqiang Mao.
Yes. Well, not Zhiqiang, but sorry, Cuizhu Chang. Cuizhu. So, I'm sorry, Cuizhu. I just haven't pronounced your name for a while, but I'm thinking about you all the time. So this is Professor Chang's work. I'm sorry. Okay, so Professor Chang's work actually demonstrated that you can indeed induce non-trivial topological state by magnetically doping bismuth telluride. And here we're trying to induce an intrinsic symmetry breaking by having a magnetic manganese layer in the bismuth telluride. So this is the manganese bismuth telluride. There are still 2 outstanding questions in the field. Is there really a time reversal symmetry gap in manganese bismuth telluride? And can we actually engineer this series of materials to drive a high temperature broken symmetry gap and subsequently high temperature quantum anomalous Hall insulators? So about the first question, I would really say that there's still a large debate in the field. And this actually dated back to 2019 when there were a couple of high profile papers published in different journals. And people find that in some studies there is a gap, and in some other studies there doesn't seem to be a gap. And that's a debate in the field. And of course, this leads to different scientific agendas, so the debate is rather intense. And also, people also discover a really peculiar so-called bulk band. And this bulk band actually has a splitting when you enter the magnetic phase. And what is the origin of this bulk band is really up for debate. So I'll really try to go through our data and highlight some of our discoveries, but Kevin, please stop me when the time is up. So this is our high resolution 6 eV ARPES. This is using one of our beamlines. And you can really see that this is fantastic data with very high quality. From first glimpse, it seems we do not really see a gap in this cross feature, which is a topological surface state. I should mention that this is a work led by my postdoc, Chen-Hui Yan, and we're preparing a manuscript on this. But exactly how small is the gap? So we're not satisfied with just saying gap or no gap. We really try to give a quantitative bound. So maybe we cannot give an exact value, but we try to give a bound. And the first thing I want to report is that there is a very interesting contrast between 6 eV laser ARPES and helium lamp-based ARPES. And from this comparison, by the way, this is on the same sample, so there's no issue of sample quality. From our helium lamp, you can see this massive gap of 150 MeV. But obviously, that's not quite the intrinsic gap because the helium lamp is basically not sensitive to the topological surface state. So this comparison actually resolves part of the debate in the literature. So we should really focus on the 6 eV ARPES. And then from this dispersion, how do we say there's gap or no gap? And what we do is that we try to perform a detailed quantitative fitting of the 6 eV band dispersion and try to fit it using various models to give some kind of evaluation of the gap. And we do both the linear extrapolation as well as a more complex model fitting. And these fittings give us a number in the range of 1 to 3 MeV. And to remind everybody, this is below our energy resolution. So basically, that's why we cannot resolve the gap. But what we can say from this analysis is that gives you basically an upper bound of the gap in the surface state. We'll skip this slide. I'll just quickly mention that we also performed something called circular dichroism on manganese bismuth telluride. What is circular dichroism? So basically, you use the polarization control of your laser beamline and try to do the ARPES study with both left circular polarized light and right circular polarized light. And then you do the contrast. You basically use the difference divided by the sum. And this has been demonstrated by other studies to be a proxy for spin texture. So for the time being, we're going to look at it with the same lens as a spin texture. And what we see is very interesting. We actually see that there's not only the surface state that's spin polarized, but there are also the so-called bulk states in the literature. We are going to call it quasi 2D states. These quasi 2D states, which are very sharp and very distinguishable, also have a spin texture. And their spin textures actually seem to largely agree with the spin texture on the surface state. So this is a mystery. Not only are these not bulk bands, there are surface-related bands. I'm sorry, there are quasi 2D bands, but also they have a spin texture. So what are they really? And we have a few scenarios. This includes Zeeman splitting, Rashba splitting, band folding due to the enlarging unit cell in antiferromagnetic state. And of course, there's more exotic scenarios due to the bulk surface hybridization. And by directly comparing the circular dichroism, which is a proxy of the spin texture in this case, with the sort of scenario in different predictions, you can immediately see that none of the individual mechanisms can explain this very well. For example, the Zeeman splitting would have a spin texture in this form. The Rashba splitting would have a spin texture in this form. The band folding should not give you any spin texture fundamentally. So you would have a hard time using individual mechanisms to explain the existence of these quasi 2D bands. And this is indeed a work in progress and a work in collaboration with Professor Chaoxing Liu and his group, as well as Professor Binghai Yan from Weizmann, that we proposed a new explanation based on quantum well states. And this is, in my language, would really be a cooperative interaction that combines quantum well states, Rashba splitting, exchange splitting, and surface time reversal symmetry preservation. Excuse me. So you need not only one single channel, you need them to actually work together to reproduce the experimental observation. And this is, excuse me, this is the results that's been produced by Professor Chaoxing Liu and his group. And you can see from these results, we can directly see the 2D nature of these bulk bands because these are basically quantum well states. And they have temperature-dependent splitting because they also undergo an exchange splitting. And this theory also partially explains the spin texture of the 2D bands because they have some spin-orbit coupling from the Rashba splitting. But I would also say that it only partially explains. The spin texture does not agree with the experiment exactly. So with the limited time, I'm going to skip the 147. I'll just quickly discuss our temporal engineering. And this is our time resolved studies to resolve the unoccupied states in manganese bismuth telluride. For this study, we used our time resolved technique, and it was led by my student Nicola and Sebastian. We basically shot movies of electronic structure from both undoped manganese bismuth telluride and antimony doped manganese bismuth telluride. And the first observation you can immediately see is that you can clearly see the occupation of the normally unoccupied states of this band structure. And that's the first accomplishment, that we can directly induce the unoccupied states very clearly. There has been some literature studies in using time resolved ARPES and manganese bismuth telluride. I would say that our spectrum seems to be very high quality compared to the studies in the literature. But there's also something that's very peculiar. So if you give me 1 or 2 minutes, I'll bring it up. So on antimony doped manganese bismuth telluride, this material actually has a gap in the surface state. And so far, there's no understanding on why there's a gap. And we performed this pump probe study so that we can actually perturb this material in a time domain. And we're hoping that this can shed some light on the origin of this gap in the surface state of antimony doped manganese bismuth telluride. The big question is whether that's actually the broken symmetry gap. So that's what we did. We tried to compare, so this is a time resolved EDC, it's a time resolved spectrum at gamma for different delays. And what's really interesting to us is that we can substantially increase the electronic temperature. We can increase the electronic temperature up to 1,000 Kelvin. But the gap between the upper Dirac cone and the lower Dirac cone, in this case, we actually call this conduction band and valence band, this gap is basically unchanged. So that's very surprising. This would be consistent with equilibrium ARPES studies using the temperature dependence, where they also saw no temperature dependence of the surface state gap. And ours basically pushing this to an even higher limit. We went to 1,000 Kelvin. And this suggests a topologically trivial origin of the surface state gap. And I would also remark that it may be topologically trivial, but not trivial at all, because if you think about even a semiconductor gap, if you go to such a high temperature, the gap should change. So there's something very peculiar about the opening of a gap in this antimony doped manganese bismuth telluride. That's the last slide, and I'll stop here. Basically, I used the 2 examples to demonstrate the vision of spatial temporal engineering of quantum materials. And I hope I have convinced you that that's a really useful tool. It's a futuristic perspective to engineer materials in spatial and temporal domains. I'll stop here for questions.
Thank you, Dr. Yang. If anybody would like to ask a question, you may temporarily unmute by pressing your spacebar, or you may physically unmute by hitting the microphone.
Can I ask a question?
Please.
So very nice talk, by the way. So I'm trying to think about the surface states that you showed in manganese bismuth telluride 1,2,4 compound. As you cool down, one expects very naively broken of the time reversal symmetry, right? And therefore the opening of a gap in the bulk bands. But your data and a whole bunch of other data have shown that the surface states is still there. So I'm not sure if I got this right, but are you suggesting that somehow there's some coupling between the surface states and the quasi 2D bands that somehow preserved the Dirac cone?
That's a great question. And
I've sort of, somebody hand waved it something to me that because somehow the spin on the surface isn't really as a cartoon drawing of up, down, they reconstruct in some complicated way. And that's why the surface states are still there.
Yeah.
But you seem to have a different interpretation in mind. I want to
let's actually go back.
your brain on it.
Yeah, let's try to go back to this. Yeah. So you're absolutely right that we don't seem to resolve an obvious gap in a surface state. Actually,
right.
The earlier slide is even more telling. So
right, you've just convinced us that the gap is small, right? There isn't a discernible gap.
Exactly.
Right.
Exactly. So I think there are a few levels of thinking in this problem. First is whether the time reversal symmetry is actually broken. And to that, I think at least in the bulk, there are numerous studies, not from ARPES, but from diffraction experiments. So people can actually detect the formation of antiferromagnetism. So
right.
AFM is there. And the second level of question is whether there's a gap in the surface state. And from this study, I think the most technically correct answer I can give you is that if there's a gap, it's less than 1 to 3 milli. It has to be a very, very small gap. And there, I think, is a big question. Why does this so drastically differ from theoretical predictions? By now, all the theoretical predictions have, assuming that you have perfect AFM state, would predict a gap at least on the order of, 40 or 50 MeV. So somehow theory is not working quite well over here. And I would say the most likely scenario is that, in my opinion, is that the spin configuration on the surface is different as in the bulk. I think we resolved this quasi 2D bands, but these quasi 2D bands are also in our model, sort of surface related, but they are not only on the very top surface. If you think about it, it's actually, so in our picture, this is actually a quantum well. So in a quantum well, your states are quantized. So depending on the levels, you have different kind of spread of wave functions. So in our language, I think this quantum well states is different from the surface state. But what exactly happens on the surface that kills this substantial, broken symmetry? That's the part I could not answer. I think the best I could answer you is it's probably not as strong as what the theory suggests. Yeah.
Thank you.
Yeah.
Anyone else online? Okay, if not, I'd like to thank Dr. Yang, and I'm sure that if you have other questions, I'm sure you could contact him offline. Thank you so much for visiting our 2DCC webinar. Thank you, Dr. Yang, for presenting, and we hope to see you in the future.
Thanks, everybody. Thanks, Kevin.